Yeah. But where is the? Yeah. One sec. Yeah. No. Here. Here is. Okay.
Okay, everyone, welcome back to the afternoon session. Go ahead.
Yeah, so let me continue. So we have defined the Dirichlet Neumann map. So let me remind you here is have the divergence gamma gradient u equal to 0 on omega u at the boundaries f. And we have this quadratic form. So gamma is strictly positive in all of this. And that's equal to the Dirichlet Neumann map F. This is surface mesh. Okay, so if U is sufficiently regular, you can define this to be gamma times the normal derivative at the boundary, right? So the inverse problem is, does lambda gamma determine gamma in the interior? That's well, everywhere. Okay. So it has several parts, uniqueness, stability, reconstruction. So, okay. So with this generalization, and then the next result for the nonlinear problem, suppose gamma is sufficiently smooth. This means all the derivatives are continuous up to the boundary. Then, you know the Dirichlet Neumann map, that you can recover all the derivatives at the boundary. So this is called boundary determination. It's useful, as we are going to see, although it's just at the boundary, it's not in the interior, it's still the Taylor series of gamma at the boundary. You have less regularity, then you can determine as many derivatives as you have at the boundary. And I'm not going to give the details of this. One of the proofs is that, for instance, for gamma equal to 1, we know, and you have the upper half plane, we know that this is the square root of the Laplacian. And this is an example of what's called a pseudo-differential operator, or a singular integral, the order 1, and this proof was proved actually by Calderon. It's a general theorem about the part of the Calderon projector, but that this means in coordinates, the boundary is given by xn equal to 0 locally. So, you can flatten the boundary locally near a point that looks like this. This is again xn, x prime, some coordinates xn, x prime. And then the boundary is locally xn equal to 0. So you flatten the boundary. And this is the expression for the Dirichlet Neumann map. We saw this in the morning, that for the case of gamma equal to 1, this was modulo C prime. And then in general, this will have an expansion of gamma at the boundary, xn equal to 0 times modulo C prime, like we had gamma is 1, that's the term we had before. And this is homogeneous of degree 0 in C prime. Positive homogeneous of degree 0. That means if you take multiple lambda here, it comes out as a lambda is of degree 0, so it's the same. And the j's term is you have a lambda here. Why does it move? Then you get lambda to the minus j, if lambda is positive. keeps me moving the page. So this is I don't know what to do with that. And from this term, you have to do the computation, and we can recover all the derivatives of gamma at the boundary. So in particular, if the gamma is real analytic, means the Taylor series converges, then you have uniqueness. Right? But that's just from the boundary determination. It's not interior determination. Okay. By the way, the slides are going to be available on the website of the conference. I will also give some notes with more details of sometimes the proof. Here I just a sketch of the proof. This is not the main. This is an inverse problem for a linear equation. I want to get to nonlinear, so this is just a review for the linear case, linear equations. Okay? And so for the uniqueness, many years ago, before a lot of you were born, if gamma is sufficiently regular, this is in dimension 3 or higher. I think Rui here will talk about the two-dimensional case maybe tomorrow, right? No? Why not? I thought you said you would. And they are positive, then if the Dirichlet-Neumann maps, the conductivities are the same. This is uniqueness result. And the regularity, in dimension 2 is different. So I thought she was talking about this, but anyway. I will mention the two-dimensional case. When you have this, then gamma 1 is equal to gamma 2. That's uniqueness and has been extended to regularity in different spaces. So let me mention this one. That's believed to be the optimal result in dimension 3 or higher, not in dimension 2. So that means one derivative in Ln. And Haberman proved this as a very nice result in dimension 3 and 4. And another important case is proved by Caro and Rogers in all dimensions, that if the conductivity is Lipschitz, meaning one derivative is in L infinity. And all of these results use complex geometrical optics solutions. And a reconstruction method was given by Nachman using, again, complex geometrical optics solution. Is the idea of using the idea of the uniqueness proof. Stability was done by Alessandrini. That means if these are closed in certain topology, then the gammas are closed. A numerical method had been developed using complex geometrical optics solutions by these authors at different years and so on. So in this case, of course, you can only take finite number of measurements. Okay, so what are the complex geometrical optics solutions? So in all these papers that I mentioned here, all of this, except for this one, use the reduction to the Schrödinger equation. So that's why you need regularity. You make this transformation, use square root of gamma times W, then the equation is transformed into, this is the Schrödinger equation. So for instance, you can put Q minus lambda squared, that's the potential. But the potential in this case is very explicit, is Laplacian of square root of gamma over square root of gamma. This is an exercise to prove that you make this transformation, this is the equation that you get. So we can consider actually more general problem. Even if Q is an L infinity, say, bounded and measurable, but may not come necessarily from the conductivity, it may not be of that form. You can consider this problem As long as this has a unique solution, you can define the Dirichlet to Neumann map to be just the normal derivative of the solution. And of course, there is importance of this is because there are other problems that can be reduced to this, or when you want to consider inverse scattering, is for the Schrödinger equation. So you have Q minus lambda squared here, the Helmholtz equation and other equations. So it's not just a generalization by itself, it appears in many other problems. I will mention some of them. So this is the problem I'm going to consider, the Schrödinger equation. And this will imply the solution of the problem for the conductivity. Even you can take a complex potential. So Q can be complex value, has a real and imaginary part, which in this case is purely real. Gamma is real, it's a positive function. And here is clearly why you need C2 or some regularity, because you take the Laplacian, you lose a lot of derivatives immediately. So if gamma is not sufficiently regular, this will have a lot of singularities. And so that's the problem when you reduce the regularity of gamma. And then there is this identity, which is easy to prove. It's just the Green's theorem, Q1, U1. So this is an important identity. Q1 minus Q2, U1, U2. Equal integration over the boundary. Lambda Q1 minus lambda Q2. U1 at the boundary times U2 at the boundary times ds. Sorry, didn't fit in one line. Yeah, this is very simple to prove because Q1, U1 is the Laplacian of U1. Right? UI is a solution of the Schrödinger equation. I equal 1 to 2. Q2, U2 is the Laplacian of U2. So this is another homework, prove this identity. And then you apply the Green's theorem. This is Laplacian of U1 times U2 minus Laplacian of U2 times U1. By Green's theorem, you get the normal derivatives, and then you can pass, you can pass one of the lambdas to the other side. So you get this identity exercise for the discussion. And in fact, if this is the same, then lambda Q1 is equal to lambda Q2, so this is 0. And we come to the familiar problem, is the product of solutions, but now are the different equations. You have U1 as a solution with the Q1, U2 is a solution with the U2, equal to 0. So the goal is to find many solutions of this equation. And then the products, if the products span a dense set, then Q1 will be equal to Q2. That's the uniqueness, and stability will be very similar if lambda Q1 is close to lambda Q2, so you have an estimate for this. And then by plugging in the CGO, the complex geometrical optics solution that I will define, you will get an estimate for Q. Because this is linear in Q. U1 depends non-linearly on Q1 because it's a solution of this equation. We don't know how it depends. But then this is the important thing of this identity. This is linear here, and this is linear here. So the non-linearity is concentrated here in the product of the solutions. So the idea, as in Calderon's computation, Calderon's linearization has some function h, gradient of u times gradient of v for the same equation. Here is different equations, but it's very similar. You're doing something very similar, right? Very similar idea. Okay, and this here it comes the CEO solution. This is what I was explaining before. Calderon considered complex vectors so that rho dot rho is equal to 0. Remember, and if you take the real and imaginary part, the length of the real part has to be equal to the length of the imaginary part, and they have to be perpendicular. So these are the waves that you consider in the case that gamma is 1. For elliptic equation, this is an elliptic equation like a Laplacian. There are no waves. This is not a wave equation. However, this plays the analog of the analog of waves. So one should think of this as waves for the elliptic problem, the analog of waves for the elliptic problem. But these are not just oscillating like in the case of wave equations. It can be exponentially decaying if x dot eta is negative. It can be oscillating. That's the standard type of waves when eta is equal to 0, and it can be increased exponentially when x dot eta is bigger than 0. And so this is the reason to reduce it to the potential is because we want to consider the potential as perturbation. And these solutions exist in every dimension. You take again a vector so that rho dot rho is equal to 0, so that the exponentials are solutions of the Laplacian. And then for rho sufficiently large, you have solutions of the equation that behave like these exponential solutions of Calderon when the norm of this in L2 goes to 0 as rho goes to infinity. So let me write it here. This is the main thing I wanted to point out about Calderon's problem. Is as I mentioned before, the point of view of Calderon is to find solutions. So this is what we're doing here. So if Q is in L infinity, so it's a bounded potential. You can find, given rho in Cn, this has complex components so that rho dot rho is equal to 0, and rho is non-zero. We can find M sufficiently large so that if rho is bigger or equal than M, so the solutions exist for large complex frequencies. This is called a frequency. There are solutions of the Schrödinger equation on omega in every domain. You can take any domain that you like. We're taking L infinity here of the form, let me call it U sub rho, U rho equal to e to the x rho 1 plus psi q of x rho with the norm. In fact, I want to make a more precise estimate. L2 of omega is less or equal to a constant over modulo rho. So it goes to 0 as rho goes to infinity. So again, the point is that you can find solutions that behave like these exponentials. And this is a perturbation of the Laplacian. That's why you reduce it to the Q here. Okay, so let me show you the proof of uniqueness, and similar is for reconstruction. I will mention this in a moment. Let's prove this in dimensions bigger or equal than 3. So this only works in dimension bigger or equal than 3. In dimension 2, you have to do something different. have Q1 minus Q2, U1, U2. So you take solutions like this, where you fix the direction K. You need rho 1 equal to 0, rho 2 times rho 2 is equal to 0. So I'm going to use the fact is dimension 3 or higher, so this factor K. So I'm going to have an additional vector L. So there is eta, L, they are perpendicular to K. All of these are perpendicular, they form an orthonormal system. And the length of the real part has to be equal to the length of the imaginary part, which is given here. So I substitute these solutions here, and then I get 1 plus IQ1 plus IQ2 plus the multiple. But now I let this variable go to infinity, L go to infinity. And I can do it because I need rho large. I need rho large, and the length of rho is eta squared plus k squared plus L squared. So if L is large, rho will be large. So let L go to infinity, so this variable goes to infinity, but I fix k. I can fix k here. Let this go to infinity. The eta also will go to infinity. So this goes to 0 because of this decay here. This goes to 0, and the product goes to 0. This is just Cauchy-Schwarz. And then you get, again, the Fourier transform of Q1 minus Q2. I didn't arrange the vectors as well as before. Minus 2k equal to 0, therefore Q1 equal to Q2 in omega. It's a very similar idea to Calderon's, except that you need these solutions. These are complex geometrical optics solutions. Questions? Yes? No, I mean, you have to show that there is this remainder. It goes to 0. For rho sufficiently large, we can find solutions so that this decays. Not all the solutions will decay, right, as rho goes to infinity. Okay, this is coming back to the point I said earlier, that you need to know more than existence and uniqueness of solutions. We need to find more explicit things, how things depend on the coefficients. And this is the type of solutions that help for this problem. And tomorrow we'll talk about real geometrical optics that are used for the Gelfand's problem. But this is for uniqueness, and for stability, again, you plug in the same type of solutions here and here, here and here, and then it's more technical because you need to estimate. You have to estimate this with the solutions here, and then you get an estimate for the difference of the potential. And for reconstruction, it's the same idea. You put Q2 to be 0, say. You're trying to reconstruct Q1. So U1 is the solution of this equation. Again, this is known. It will be lambda 0. U2 will be known. You just need to show that you can recover U1 at the boundary from the Dirichlet to Neumann map. And this can be done. But it's the same. You use the same type of identity and using also this complex geometrical optic solutions. So that's the key. And for many elliptic problems, this is the key. To find solutions of this type or another type that have the behavior that you need. Okay, so these applications of this are numerous, which have shown that this, for the Schrödinger equation, the Dirichlet to Neumann map determines Q. This is dimension bigger or equal than 3. Again, I'm going to talk about the two-dimensional case. It has different features. This proof does not work in 2 dimensions. I should have mentioned this. Because if K, you have only 2 vectors You cannot have more, you need two vectors perpendicular. If you let one go to infinity, the other has to go to infinity. So you don't have any freedom in dimension 2. So this proof does not work in dimension 2. You need to do something else. And I will explain what are we going to do. But in dimension 2, it looks not intuitive. There are more complex geometrical optic solutions, not of this type, but with a different phase here.
The linearized problem.
Sorry?
The linearized problem.
Yeah?
That works too.
Yeah, it works in any dimension, yeah. The linearized problem, again, I repeat, does not imply anything. So one application is what's called optical tomography, was called the diffusion approximation. Instead of having electrical currents, where is the here, you take a laser beam and you put light. And so this is the frequency. This is different physical meaning. Before we had the conductivity, but the equation is very similar. We had D, the diffusion coefficient, and sigma A is called the optical absorption. You can see that this part is very similar. The other part, you can put it in the potential. Because we can take complex potential, this is real value. If the frequency is non-zero, you can recover both using the same ideas that I had before. It's exactly the same. The diffusion coefficient and the absorption, optical absorption. They are both real. That's why it was important to recover a complex potential. If omega is equal to 0, then you don't have the freedom. You can recover one of them, either D or sigma A. An optical tomography is used in hospitals to monitor the brain of premature babies. You want to see how the brain is developing, whether it's bleeding in particular, or things of that sort. And this is what optical tomography is very good for small objects. Because light, this scatters after it penetrates, it scatters a lot. So it cannot be very large objects, but for premature babies, this is good. But there are other applications. For instance, for optics, you have the Helmholtz equation, frequency k, where this is the index of refraction. And the same problem, from the Dirichlet to Neumann map, you can recover the index of refraction. The Q is equal to this. This is a fixed energy. It's an important thing. We're not taking the energy to be large. It's just fixed. For the acoustic equation, propagation of sound, rho is the density and k is the compressibility. These are both real. It's not like the case that we had before for optical tomography. Now you're sending sound waves, and P is the pressure. And then using from the Dirichlet to Neumann map that you can associate to this, you can recover one of the two for one frequency, and both of them you have two frequencies. You know it for the Dirichlet to Neumann map for omega 1 and omega 2. For quantum scattering, so you send particles, and then they scatter, and you have fixed energy. This solves a problem that was not known before. You have the Laplace minus Q minus lambda squared, but this is fixed. This is like a potential. Then you can recover the potential from the scattering operator at fixed energy. For Maxwell equations that describe electromagnetic waves, in the isotropic case, you have the parameters epsilon, mu, and the density, the electric permittivity, the magnetic permeability, and the density. You can reduce this. This was done by Uhlmann Somersallo. to Laplacian minus Q, but this is an 8 by 8 system. Maxwell equations is a 6 by 6 system with these divergence equations. You can write it as a Schrödinger equation, and this is a matrix. But the method that we have also works for Schrödinger equations, matrix Schrödinger equations. And also for this, but this is the, I'm not going to describe it for photoacoustic tomography. Okay, so Sebastian was asking me about other phases. So there are, there is a big difference between dimension 2 and higher dimension again. We can have, this is the ones we consider. There are other phases that you can take, more general phases. This is not going to be linear anymore. This depends linearly here on X. This will be non-linear. But it has a real part phi and an imaginary part psi. There is an amplitude here that you can choose. It doesn't have to be 1 like here. And then there is a remainder. And tau is a real parameter that goes to infinity. Corresponds in the previous CGO solutions as modulo of rho. And what you need is to solve this in order to kill, when you plug the Laplacian minus Q to this, in order to kill the term of order tau squared. This is another exercise. You need this condition that the gradient of the real part has to be perpendicular to the gradient of the imaginary part. We had this here. For rho to be 0, you need that the real part, the length of the real part has to be equal to the length of the imaginary part. That's the gradient, right? The gradient is just rho. And they had to be perpendicular. But this is now a system in 2 dimensions where we can solve this by just taking phi to be any harmonic function and psi to be the harmonic conjugate. I will explain this in more details later. In 2 dimensions we have a lot of solutions for this eikonal equation, but in higher dimensions we have very few. This is the linear case here, and there is this one where it's called a limiting Kahneman weight. This comes because of Kahneman estimates. But it's the log of x minus x0, where x0 is outside the convex Hall closure of the domain. So this is it's called a limiting Kahneman weight, and in that case, you can solve this system. And I can solve explicitly, I can tell you explicitly what is psi. So these are solutions that are more flexible because, for instance, in this case, in the ones we had before, for the real part, these are like plane waves. The first is x dot eta, suppose rho is eta plus ic, like I didn't write it here. Then these are plane waves. So the level sets come from planes. You take planes coming in, plane waves, and they have an oscillatory part too. Right? But here, when the phi is constant, the level sets of this is constant, is x minus x0 modulus a constant, there are spheres. So you take a point outside the domain and you probe it with spherical waves. It's called complex spherical waves. And that leads to new results. So these are the solutions. Phi is the log of x minus x0. These are complex spherical waves for that reason. Before you have plane waves, complex plane waves. And the theorem that one can prove using these things is the following. Suppose omega is strictly convex. There is a more general theorem, but I'm not going to describe. Suppose the Dirichlet to Neumann maps are the same only for measure at an open, arbitrary open subset of the boundary, non-empty. Before we had the measurements everywhere. This is called partial data. Suppose you have that, then you can conclude that Q1 is equal to Q2. This is in dimension 3 or higher. Questions?
The decay of remainder is not 1 over tau?
The decay remainder in this case is 1 over tau. Yeah. Yes, the same as we had before. Yes, I should have mentioned that in the L2 sense. So thank you for the question. Any other question? But there is not much flexibility in dimension 3 or higher. In dimension 2, there is a lot of flexibility. Okay, I'm not going to talk about this because it's very technical. It's in the notes, and you have any questions, it will be in the notes available. As I said before, my intention for this talk is just to give a survey of the solutions of the Calderon's problem. It's not the purpose, but of course I'm happy to explain anything. Also, there will be notes with more details. Actually, a more general theorem can be proved, as I said before, but the point, this is very similar to what happens in optics. To solve this equation, the side to solve this equation is the distance between this vector in the unit sphere to omega, which is to the sphere, the distance of this vector to the sphere for any point here. So this is called, suppose you shine light. This is the front face, that part is illuminated, and you have the back face, the part that is not illuminated, called is in the shadow. And the amplitude of these waves, of these solutions, where is it? The amplitude can be found by solving a Cauchy-Riemann equation, this like d bar equation. So this is gradient phi plus I gradient side is times the gradient is equal to 0. It's called the transport equation in this case. Suppose this is like this, because these are orthogonal and they have the same lengths, you can transform this at dx1 plus I dx2. This is what's found in analytic functions. So it's a Cauchy-Riemann equation in these planes. Remember, these are two orthogonal vectors. They have the same length. So in this way, we can find the solution of the amplitude. This is called the Conal equation, and this is transport equation. We're going to see this again for the real geometrical optics tomorrow. Questions? Yeah, so that's why it's very special. In general, in dimensions 3 or higher, you cannot solve this unless you have some conditions. And this came from phi being a limiting Kalman weight. I mean, we had to find the side, right? The side is very explicit. And this is another exercise show that this solves this. This is the distance between this vector and the sphere. Okay. So, so let me tell you some applications of these solutions other than the partial data problem. You can determine inclusions. You can probe an object with spherical waves. For instance, you have an inclusion here where the conductivity changes. So this is gamma. In this case, the uniqueness result is not applicable in dimension bigger or equal than 3. You have two conductivities here, and they are different. So this is called an inclusion. There's a jump in the conductivity. This is very common. So what we're going to do, we're going to send these complex spherical waves to recover this, the places where it jumps. So where it's jumping and how much is jumping. So you want to see how much is gamma 2 minus gamma 1 at the boundary, here, the jump here, and also the location. So this is, it's called V. You want to find B. You want to find the strength of the jump and also the location of the jump. This is called inclusion. There are also cracks where the flux is 0. All of this type of, and you can have an obstacle also where you have reflection, so on. For the conductivity equation, this was done here, and the Helmholtz equation, elasticity, and for Maxwell equations, and there are other, elasticity also has been done and so on. So this is very useful for determining, because it gives you more freedom. You can send spherical waves. You can also send plane waves. You can use plane waves to probe the obstacle as well. This is also useful, in particular, to detect convex domains here. So let me show here how it's done. This is conductivity 1, conductivity 4. These are the points x0, and these are the complex spherical waves. And you can see that the domain where it jumps is being found there. Okay, questions? So how much time do I have? Sorry? 15 minutes? Okay. Questions before I continue? Of course, I didn't give the proofs of this. I just wanted to give the idea of the new. So there are two CGO solutions, two types of CGO solutions that we have in dimensions bigger or equal than 3 that we have considered. And this is the important part. I mean, there are technicalities on how smooth the potential is and so on. These, of course, are important questions, but the key idea is to find these solutions for these elliptic problems. And so these are CGO. This is in any dimension, e to the x dot rho 1 plus psi q. This goes to 0. We didn't use the fact that decay is like 1 over modulo rho, right? We only use that goes to 0. And in n bigger or equal than 3, this tau phi plus I psi, an amplitude here, plus a remainder term. This is also goes to 0 in the L2 sense. And the gradient of phi is perpendicular to the gradient of psi. The length is the same. And phi, we're talking the log of x minus x0, where x0 is a point outside. So these are spherical waves coming from the outside. Is in the complement of, let's say omega is convex, omega closure. Right? Okay, so how about the two-dimensional case? Of course, the physical problem is really in dimension 3 or higher, because that's what you want to solve. The currents don't stay in a plane. They go all over the place. Remember I showed the picture at the beginning? So even if you have conductivity that depends on two variables, it's not helpful because the currents go all over the place. You really have to consider the three-dimensional case. So for uniqueness, For C2 conductivities, Nachman proved the uniqueness result, that if the Dirichlet and Uhlmann maps are the same, then the conductivities are the same, and also reconstruction and stability was proven by other authors. Okay, and with Brown, we improved this to Lipschitz conductivities. But a very nice result of Astala and Paivarinta using quasi-conformal maps. So here does not use the reduction to the Schrödinger equation, that because you lose regularity. And also this one does not use reduction to the Schrödinger equation either, because here we have only one derivative. This is in W1 infinity. So if we could do that in higher dimensions, we could improve the regularity, but we don't know. This uses quasi-conformal maps. So this is a very nice result. Okay, so remember the Dirichlet and Uhlmann map is defined this way. So now gamma is an L infinity, very general gamma, compared to dimension 3 or higher. There is a question how lower the regularity can be in dimension 3. Can we do L infinity? Let me add some conjectures here that might be useful. Let me leave the CGOs here. So in dimension bigger or equal than 3, so lambda gamma determines gamma. You have to assume that gamma is in W1 n of omega. So this has been proven already in dimensions 3 and 4. And there is a reason for this. This is one derivative in Ln. Okay, but a problem here, it has been already proved in dimension 3 and 4. So of course, those are the 3 dimensions is the main one. But the problem is it false for dimension for gamma below W1n. So this is part of the conjecture that this is optimal. Nobody has found a counterexample in dimension, this is in dimension 3, bigger or equal than 3. So this is you have a problem to work on. That will be, it's very difficult to find counterexamples because you have to produce the same current flux, the same normal derivative, no matter what you have. So it's not so easy to find counter. It's not that you have one solution, like unique continuation, and you're trying to prove there's 0 or something. You have many solutions. But also my conjecture is the counterexample is bound to be very strange, meaning conductivities that don't appear in nature. So I think it's true, and the gamma recovers gamma, if gamma is piecewise smooth. Again, dimension bigger. Dimension 2 is known for L infinity conductivities. So this is a very physical case because the conductivity, like in the human body, the conductivity, you have different organs. The conductivity changes from organ to organ, is piecewise smooth. Has some structure, right? It's not arbitrary. I mean, this is, that's what the counterexample, like many counterexamples, for instance, or non-measurable set or function which is not measurable are very strange. Most functions are measurable in practice. The same thing I think should be true because this is the physical, it's more physical case. If it is physical, you should be able to recover. That's it's this conjecture. I don't have a proof. Okay. So, but this result is very, very nice. I mean, for L infinity, you can recover. The proof again uses a lot of. The difference that here you use a lot of complex analysis. Every one of these three proofs use 2 dimensions. The fact that you have complex analysis in 2 dimensions. So, sorry? Well, this is, yes. There is it's very natural to do this for every even dimension, right? Because you have a complex structure. But even that we have not been able to do. But that will be a case to try, yeah, when you have some structure. For complex manifolds in dimension, even Keller manifold, we haven't done it. No, this is a very interesting question. So in dimension 2, there is a very nice, also another very nice result. Again, 2 dimensions, we know much more. Uhlmann, the proof. This is just for conductivity. In 2 dimensions, the proofs here don't imply the case of the potential. They're very much dependent on that you have divergence type equation. Remember, the equation is a raised here divergence of gamma gradient u can be reduced to the potential, but in order to prove this theorem, you have to use the fact that it's in divergence form. Okay, however, Uhlmann in dimension 2 proved that for any L infinity potentials, you have uniqueness. And also you can have a stability in the same sense and reconstruction. So this is again, this is the result. I mean, this is the definition for any potential here. And this is again, the crux is always a new class of complex geometrical optic solutions. So let me erase. So we have already 2. In dimension 2, you can find new classes of CGO solutions. So n equal to 2. CGO solution. Do you have time? 5 minutes? Okay. That's enough. Oh, what happened? Cannot write now. Oh, yeah, now. So let me tell you 2 types of CGO solutions in dimension 2. U tau equal to e to the tau phi plus I psi A plus remainder term. Time. So let me concentrate on the phase, where phi is harmonic and psi is harmonic conjugate. Because in this case, so that means you take an allomorphic function. Yeah, well, because in that case, phi is harmonic. That means the Laplacian of phi is 0. The Laplacian of psi is also 0, but one has d bar of 5 is 0, and the other one has d psi equal to 0, and the gradients are perpendicular. That's what we use in dimension 2, and the length is the same. So this is in dimension 2. So any homomorphic function, but you need another assumption that the gradient of phi is non-zero on omega closure. Because you need this, otherwise this condition is always satisfied. The gradient of phi is equal to 0, and you will need that the gradient of psi is equal to 0, so phi will be constant. Okay, so these are CGO solutions in dimension 2, and these were constructed in the same way that these solutions were constructed. So this is a limiting Kahneman way to call. But Buchheim, the second solutions, so these were constructed by Koenig, Sjostran, and myself. Okay. In 2 dimensions, you also have, so let me erase dimension 3 here. This is e to the tau z square, or z conjugate square times an amplitude. 1 plus a remainder. So z square, z is, or you can put z conjugate also. C is x1 plus ix2. We're in 2 dimensions. C square is x1 square minus x2 square plus 2i x1, x2. Right? And so you take this one solution in the identity, you use the same identity, but this has the gradient vanishes at 0. So let me point this out. Huh? Yeah, so you assume that 0 is in omega. In omega. Because here, if 0 is not in omega, then you use these solutions. Number 1, the gradient is non-zero. However, we want the gradient to be 0. So this vanishes. Let's call it 5 on this side. The gradient is 0. At 0. Right? But it's non-degenerate. The Hessian, I mean the second derivative is non-zero. So you consider what's called the Hessian. This is the second derivative with respect to x1 squared, second derivative with respect to x2 squared, and here dx1, dx2. This matrix, dx1, dx2, this matrix is non-singular. It's called the Hessian because you take the second derivative, let's say, of this one. The second derivative with respect to x1 squared is 0, at 0. But the second derivative with respect to x1, x2 is 2, and so it's non-degenerate at 0, right? So it's called a Morse function. Has a non-degenerate critical point. Maybe this is a little messy here. Let me. This is very nice, but the space is very little. Huh? Oh, I can move. Oh, I can move like this. How?
No,
Oh, good. The Hessian. Or say, let's take the phi of psi, which is second derivative with respect to x1 squared, second derivative x1, x2 of psi. You want to compute it as 0. It's independent of 0, so dx1, dx2, and the second derivative with respect to x2. This is non-singular. It's called a Morse function. It's holomorphic. Z squared is holomorphic function. Or as you put C conjugate square is anti-holomorphic. So this is equal to 0, 2, x1, x2, 2x2, sorry, 2, 0, right? So it's 4, the Hessian. The determinant of the Hessian is 4. So that was a new idea of Uhlmann to consider 5 harmonic and psi conjugate harmonic, that means solve this equation. And then you replace in the same identity. The identity is true in any dimension, and these are solutions. So he put e to the I tau z squared, and and the second, okay, and then when you do the multiplication, you get 2I tau x1, you cancel the real parts again, the same thing that we did before, cancel the real part, these are remainder terms. By the way, the decay, since I didn't write it here, goes to 0, but it's 1 over the square root of tau. The decay is less rapid at infinity. Then you have this integral. You don't have the Fourier transform, but you have an oscillatory integral with a non-degenerate phase function. Has a critical point at 0, non-degenerate, you can use stationary phase. So this is something called a stationary phase that I was hoping that Rui will discuss. So you can discuss stationary phase. So this is concentrated stationary phase, very useful method for computing asymptotics. We want to find asymptotics of this as tau goes to infinity. Then it concentrates at the critical points of this phase function, which is 0. And the other terms go to 0 as tau goes to infinity. So you get Q1 minus Q2 at 0 is equal to 0. It's a brilliant idea. And then to get it at another point in the domain, you change it. You change z to z minus z0. It's exactly the same thing. And you get Q1 minus Q2 at the point z0. Z0 equal to 0. That's the end of the proof. So it's this idea, he had a new idea here of consider CGO with, this is holomorphic. We knew that holomorphic functions were good as long as the gradient is non-zero. He showed that as long as you have a non-degenerate critical point when the gradient is 0, it's still okay. Okay, so let me finish with this. Questions? Because we have discussion now, so you can ask. So these are the two solutions, minus tau z squared, so you cancel the real part again. And then you get this. Oh, you get this, 2 times. This is also non-degenerate. Depends on which ones you cancel. We were canceling the real parts of this, and then you get this, right? It's a non-degenerate critical point. Stationary phase, if you don't know it, I highly recommend that you study it. And there are many, I can give you a reference if you want. Okay. So finish with that for today. Questions? Just let me know.
Will Uhlmann approach for two-dimensional case with harmonic conjugate for 3 and upper?
No, we have tried, because after he came up with this, we have tried. You know, the natural idea will be to use some Dirac operator in higher dimensions, and you know, but no cigar. Yeah, no, it's a very natural question. Right? Yes. In that's what I was saying earlier, that in 2 dimensions, these exponential solutions that we had previously at the very beginning, they are much less in 2 dimensions than higher dimensions. But there are a lot of other CGO solutions because you have complex analysis. So when you have other structure, like 4 dimensions, you were asking even dimensions, it could be. You know, try. But, yes?
So in that equation, is the idea that as you let tau go to infinity, you get like the x1 Fourier slice?
No, you get the Q1 minus Q2 at the critical point. It's very different than the Fourier transform. So everything, the stationary phase tells you that, of course, there are other lower order terms in stationary phase. The highest order term, the main contribution comes from the critical points. If this phase has no critical points, then you can show that this is rapidly decaying.
But from that equation, the next step is to let tau go to infinity, you get the interval q1 minus q2 times d power 4i dx1 x2 is equal to 0, right?
No. This is concentrated at 0. You get Q1 minus Q2 at 0. Let me do a stationary phase here, since you're asking. Oh, I can go further. So this is let's say, forget about the tau, doesn't matter. E to the I tau x1, x2 times Q1 minus Q2 times 1 plus R1. The same what we had before. But before we had the Fourier transform, right? But here we don't have the Fourier transform. The Fourier transform is x dot c. And that's the gradient of that is non-zero. So stationary phase tells you that, so this is stationary phase. And Rui will explain this in more detail. Is Q1 minus Q0, Q1 minus Q2, evaluated at the critical point. Everything is concentrated at the critical point, at 0. And this is tau to the n over 2, so tau in dimension 2, plus terms of order or lower order. So you multiply by tau, then you get as tau goes to infinity, this goes to 0. You get Q1 minus Q2 at 0. So everything is concentrated at the critical point. Because look at the following. Suppose you have e to the I tau times some function, let's call it g, times an amplitude, let's call it b, so not to confuse, equal to 0, right? And suppose that the gradient of v is non-zero. Then you can integrate by parts many times. This is rapidly decaying if gradient of g is non-zero. If there are no critical points, because you just do this trick of, you differentiate the gradient of e to the I tau g times I tau is the same as e to the I tau, sorry, a gradient of I divided by I tau is e to the I tau g times the gradient of, sorry, the gradient divided by gradient of g. Let me, yeah. Right? You have this. So you replace this because the gradient is non-zero, right? So you replace this by this and then integrate by parts. You integrate by parts the gradient and put it here. And then you repeat this process many times. And then you're going to get that this is rapidly decaying. So if there are no critical points of the phase, then this is rapidly decaying. And here, there is a critical point. A stationary phase tells you that everything is concentrated at the critical point where the phase vanishes. Okay? So this is stationary phase. A good reference for this is the book by Grigis and Shostran, Macrolocal Analysis of Differential Operators, or something like this. Yes, this stationary phase is used a lot in asymptotics, to find asymptotics of gamma functions or Bessel functions and things like that. You use stationary phase. Or steepest descent, that's another method. But it depends on the critical points of the phase function. Right. Yes. Questions? Yes?
So I'm having trouble understanding the definition of this phase function. So what I see is you sort of grade two waves with the opposite amplitude, the same oscillation which grades resonance.
Yes.
But like in the real case, your phase function is supposed to, it satisfies Hamiltonian, so it's parameterized from Lagrangian. But in the complex case, is the complex part of your phase function doing similar things? Like for the real case, it's sort of showing you which direction you should travel. But I just don't see how that's related in the complex case.
Well, in the complex case, you do have a complex Lagrangian. Right?
So was it on the
This is generated by the plane